latest word is that the universe may be only 9 or 10 billion years old. Astronomers are perplexed. And they're building telescopes like crazy, from the South Pole to the Atacama Desert. Leveling sites for bigger and better observatories. On the volcanic peaks of Hawaii, it's almost crowded. The telescope boom is right on time, for there's a conundrum. Scientists used to agree that the universe was about 15 billion years old. In 1994, new observations shaved off some 5 billion years. But how can that be when stars much older have been observed? It's not the first time our notions of the universe have been out of kilter. The Hindus had a naturalistic view of the universe. Their world is supported by 4 elephants. The elephants stand on a turtle. The turtle swims in an ocean of milk. And surrounding everything, a giant serpent. An incredible picture, but no more so than the theories and observations of modern cosmology. It's difficult to believe the universe was born from a speck smaller than an atom, from the cataclysm we call the Big Bang. A searing burst of energy that cools and becomes matter. Is this how things began? Subatomic particles drawn into clumps by gravity. The formation of simple atoms like helium and hydrogen. Balls of hydrogen, bigger and hotter as their gravity grows. The birth of stars. Millions of stars in clusters. Billions of stars in galaxies. Our own galaxy, the Milky Way, contains 200 billion stars. One of them, our sun. A star is born from a ball of gas, squeezing denser and denser as gravity increases. Temperatures soar, nuclear fusion sparks, and the star begins to shine. In a continuous nuclear reaction, the star converts hydrogen into helium. All that prevents the star from exploding into space is the opposing pull of its gravity. But when the hydrogen runs out, the star begins to grow. It changes color. It's a red giant. With hydrogen gone, the star converts helium into carbon and then into heavier elements. In the biggest stars, when iron is formed, gravity prevails and the core collapses. The giant explodes as a supernova. Rich in the heavier elements, the debris blasts across the galaxy, material that, one day, will help form new stars. Such a blast may have kick-started our own star, the Sun, triggering the collapse of a cloud of dust and gas. More than 5 billion years ago, The condensing nebula contains everything that will make the sun, the planets, and us. As the cloud collapses under gravity, pressure builds. The center gets hotter and hotter. At a critical temperature, nuclear reactions fire up, and the sun is a star. Our sun is too small to make the heaviest elements, so the iron that flows in our blood must be imported from the debris of a supernova. Today, the sun is middle-aged, but in more than 5 billion years from now, with its hydrogen gone, our star will wane. But first it'll expand, getting redder and redder and fatter. The planets Mercury and Venus will be consumed. Earth's oceans will boil. Now a red giant, the sun will melt the ice on distant Titan. Life could well take hold on this moon of Saturn. But its moment in the sun will be brief. Its fuel spent, the sun will dim and slowly shrink. Our star will be a corpse, a white dwarf, no bigger than the Earth. Its shroud, a cloud of solar debris, a planetary nebula. By studying the color and intensity of starlight and the way stars group together, scientists have reached their understanding of the universe. These are the stars of Omega Centauri. They comprise a globular cluster, one of several that hover outside the central bulge of the Milky Way. The light from these stars reveals their chemical composition. From that, astronomers have worked out that globular clusters contain the oldest stars in the universe. And these clusters have given us a fix on our place in the Milky Way. The Sun is suburban. It lies 2/3 of the way out from the galactic center. A galaxy like our own, a great disk of stars from an edge-on perspective. The dark streak is dust from which stars are born. Older stars populate the central bulge. The very oldest form a halo round the center, those globular clusters. In the blue rim of the galaxy are younger stars. The galaxy from above, so to speak. A tightly wound spiral of billions of stars, all of them orbiting the galactic center. The spin of objects in space produces colors. It's called the Doppler effect. Apply it to a galaxy, and the stars moving toward us appear bluish. Their light is compressed. The stars moving away look reddish. Their light is stretched. It was the Doppler effect that gave astronomers the clue that galaxies rotate. In our case, it takes the Sun 250 million years to orbit the galactic center. There are millions of spiral galaxies like our Milky Way. Along the arms, pinkish clouds of dust and hydrogen gas where stars are born. But not all spirals are so tightly wound. This is a barred spiral. The center is quite distinct. Evidence is mounting that our own galaxy is a barred spiral. Some galaxies have no particular shape. Irregulars, like this, show few signs of forming new stars, and they're usually small. biggest of all are elliptical galaxies. Some are shaped like a softball, others like a football. They grow larger by devouring smaller galaxies that drift too close. In this scene, a spiral galaxy is being cannibalized by an elliptical one. At least that's one theory. The debate is over Centaurus A. Some say it's a single galaxy girdled by a dark band of matter. Others say it's two galaxies interacting. A computer shows one version. The stars and clouds of two galaxies merge to form a single entity. There's no doubt about this merger. These are the antenna galaxies, joined like Siamese twins. Run in reverse on a supercomputer, billions of years ago, they were separate galaxies. Nobody knows which, but one of these little galaxies passed clear through a bigger galaxy, a spiral. Like throwing a pebble into a pond, a wave of star formation spread outward. The big galaxy is aptly named the cartwheel. Supercomputers augment telescopes in studying galaxies. They add the mathematics of gravity, motion, and mass to observational data. Calculations show that our own galaxy may have tangled with others. Today, the Milky Way looks something like this, a galaxy minding its own business. But in the night skies of the southern hemisphere, and visible to the naked eye, are two neighboring galaxies of ours. They're called the Magellanic Clouds. They're moving from the lower left toward the center of the picture. Observed more closely, both clouds appear disturbed to astronomers, the result, they think, of a close encounter with the Milky Way. This one, the small Magellanic Cloud, is especially disrupted. And in the large cloud, the brush with the Milky Way may have triggered the birth of a profusion of stars. The Magellanic Clouds are much smaller than our galaxy. They're like satellite galaxies to the Milky Way. Billions of years from now, they may mess with us again. Beyond the Magellanic Clouds, the nearest galaxy is Andromeda. In the 1920s, it was pegged at 750,000 light-years away. Today, Andromeda is set at 3 times that distance. It's an indication of the margin of error in measuring the cosmos. But like these pictures from the Hubble Space Telescope, we're seeing ever more clearly. Andromeda has swallowed at least one other galaxy. For all the wide-open spaces in space, you can't always see clearly. Sometimes a galaxy gets in the way. If it's big enough, it acts like a distortion lens. Thus, peering through a galaxy, the Hubble telescope saw one distant quasar as a multiple image. Since the technique was discovered in 1912, stars that brighten and dim in a regular cycle have been a yardstick in measuring the cosmos. They're called Cepheids. The period of a Cepheid's pulsation indicates its true brightness, its luminosity. By timing the variations in its brightness, astronomers fix its luminosity. The farther away the Cepheid is, the dimmer it appears. The difference between the Cepheid's true and apparent brightness reveals its distance from us. Astronomers have other methods of working out distance. They measure the luminosity of star clusters and of planetary nebula, cosmic smoke rings, the debris of dying stars. More important is the flash of a supernova, signaling distance from 100 times farther than a Cepheid. Edwin Hubble said it first: the farther, the faster. The farther away a galaxy is, the faster it's retreating, the more its light is stretched into red. Hubble is the American astronomer who, in 1929, discovered the universe is expanding, powerful evidence that things began with a big bang and have moved outward ever since. Quasars are the most distant objects we see in the universe. Their light is shifted farthest into red. Their intense concentrations of energy, so bright they're visible over vast distances. Pulsars may be the hubs of remote galaxies. At their hearts, gigantic black holes release jets of energy as they devour stars. In early 1994, the Hubble telescope picked up this quasar 12 billion light-years away. It seems to be swallowing a whole galaxy. Later in 1994, the Hubble took a look at the spiral galaxy M100. What it saw threw astronomers into confusion. At the heart of M100 are the pulsations of a Cepheid. They tell astronomers that M100 is only about 50 million light-years away, much closer than previously thought. This distance, and the amount the galaxy's light is stretched into red, suggest the universe is expanding nearly twice as fast as we believed. If that's true, the universe is only 9 or 10 billion years old, not 15 as we once thought. The movement of M100 through space is possibly being speeded by nearby galaxies. Only the observation of Cepheids in ever more distant galaxies will help astronomers solve the puzzle. Why a puzzle? Because the chemistry of the oldest stars and globular clusters sets their age between 13 and 15 billion years. That's too old for a universe that began only 9 billion years ago. A younger universe doesn't allow for cosmic evolution as we know it. It doesn't give ancient superstars time to complete their life cycles and spawn younger stars like the Sun. The dilemma for astronomy is that even the most modern measurements of the universe have a 30% margin of error. To resolve the age of the universe, observers must estimate the distance to as many galaxies as possible and by as many means as possible. They must build a three-dimensional picture of the universe. It's a huge task, for there are billions of galaxies. Here, at the Schmidt Telescope in Australia, scientists have speeded up the job. Working from a photograph of a distant region of the cosmos, they position optical sensors on a template. They're fixed to spots where galaxies were recorded on the original photograph. Each sensor will detect the brightness and colors of a particular galaxy. The template is then loaded into the telescope, through which the original photograph was taken. The telescope is aimed exactly at the sector of the sky that was photographed. Precision is vital. Each sensor must pick up light exclusively from its assigned galaxy. The light from hundreds of galaxies is sampled in a single exposure, work that once took months. The distance and red shift of each galaxy is processed on a computer. It displays them as a segment of the universe, a slice of time and space, one piece of the cosmic jigsaw puzzle. Painstakingly, piece by piece, an overall picture is emerging. We know already that billions of galaxies are strung like smoky pearls through the voids of the universe. We don't know what caused this pattern. Ever more sophisticated telescopes will peer farther into space and farther back in time. This one is planned in Chile. It'll be the largest in the world, 4 optical instruments whose combined eye on the cosmos will be over 50 feet wide. It may help determine the age of the universe, but it won't see back to the Big Bang. At the earliest, the universe was 300,000 years old before it became transparent, and the first light and radiation could travel unimpeded through space. But there are other means of detecting the dawn of the universe. Cosmic microwave background radiation echoes the Big Bang itself. The COBE spacecraft has discovered ripples in the microwave background that could be the seeds of the structure of the early universe. And at the South Pole, astronomers fly in to study the infant cosmos in near infrared. This is an infrared telescope. It works beautifully here because the atmosphere is clear and dry. Water vapor absorbs infrared. At the South Pole, moisture is permanently frozen. At this unlikely location, observers collect infrared data from space, evidence, they hope, of the earliest signs of cosmic structure in the wake of the Big Bang. Wherever and however the Big Bang took place, the theory insists that a speck smaller than an atom gave rise to all matter. From that matter grew an abundance of stars. Stars that shone and exploded. Stars that seeded the universe with the elements of life. Stars that collected in galaxies. Stars that gave birth to planets, on one of which evolved creatures still struggling to discover how it all began.